Okay, so class number 2 here. We're going to build our Bobot today, and then we're going to test the servos, and then we're going to put in a speaker program that tells us if the microcontroller's been restarted due to low batteries. And then finally we'll do a little program to debug the servos. So yeah, we're going to need a little screwdriver. I'll possibly have some pliers to help us assemble the Bobot, but we might just use our fingers and a screwdriver. Okay, so inside the package you'll find the robot chassis here. It's this kind of bronze looking thing. And there'll be 4 standoffs and 4 screws and a grommet, a rubber grommet, that is this black ring looking thing. So what we're going to do is we'll put the surface side of the chassis up and then put the standoffs here on top of the surface of the chassis. And so the little screws will go in on the other side. And then the ring, the black ring grommet, goes in the middle. And the purpose for that grommet is to protect the wires. The wires are going to come up from the bottom of the chassis and in through the middle there. So that rubber will keep them from rubbing against the metal and starting to fray. Okay. So next we'll take our 2 continuous rotation servos, make sure again that they have the label saying continuous rotation on the top, and we're going to unscrew the horns from the servos so that the bare mounting is showing. And then we're going to take another set of 8 screws and nuts, and we're going to just mount our servos on the inside of the chassis as shown here, and then we'll run our cables up through that center grommet. Okay, this is just showing again that there's 2 different types of battery packs, one for the Board of Education, that would be the newer kit for those new to class, and then the older one for the homework board with the tinned wires. So if you had the What is Microcontroller class, that should be that battery pack with the tinned wires. Okay, this is just showing the bottom side. There's a couple of screws to put in the battery pack into the chassis, and then we'll take the battery pack leads and the 2 servo leads, the wires, and put them up through the grommet. And you can see on the right here they come out on the top side where our 4 standoffs are. Okay, next we'll get the cotter pin, which is shown over here in figure 3.7. And there is a 3rd wheel. It's basically just a sphere with a hole drilled through it so the cotter pin can go through it. And there'll be our 2 wheels with traction bands and a couple of screws. So we'll just shove that cotter pin through the sphere while it's in the back side of the chassis to attach it to the chassis. And then the wheels, after we have the bands on, we'll just screw those directly onto our continuously rotating servos, as shown here in figure 3.8. Okay, so this is just showing are two different style of boards. The homework board on the right over here, and the Board of Education here on the left. So yeah, there's 4 screws. We'll just put the board on the standoffs and then screw it on. And then we'll hook the servos back up like we had them previously. Right, so here in figure 3.1.2 we have the assembled Bobot with the Board of Education and with the homework board here. Alright, so when we got it all reassembled, we'll do something to test the servos. Let's just read it. In this activity, you will test to make sure that the electrical connections between your board and the servos are correct. Figure 3.13 shows your Bobot's front, back, left, and right. We need to make sure that the servo on the right turns when it receives pulses from pin 12, and the servo on the left turns when it receives pulses from pin 13. Testing the right wheel. Next example program will test the servo connected to the right wheel, shown in figure 3.14. The program will make this wheel turn clockwise for 3 seconds, and then stop for 1 second, and then turn counterclockwise for 3 seconds. Alright, so this is important after you get the program entered, but before you run it, you'll want to set the Bobot on its nose. So you'll tip it forward so that the rear wheel is in the air, but also so that the 2 powered servo wheels are in the air, so that you'll be able to just watch the right wheel turn clockwise and counterclockwise. Reload the batteries. On the Board of Education, you'll set the position, the 3 position switch to position 2. On the basic stamp homework board, we just put the 9-volt battery clip right into the prototyping area. Alright, so basically we just enter this program, and then we just look and make sure that it does clockwise first, and then stop for a couple seconds, and then turns counterclockwise for 3 seconds. And that's pretty much all there is to it. Okay, so the program's split on 2 pages here, on 83 and 84. So this first for next loop, it does a 650. The comment over here says go clockwise for 3 seconds. And then it does the stopping pulse, which was 750 or 1.5 milliseconds. It'll stop for 1 second. Notice that it only goes from 1 to 40 rather than from 1 to 122. And then this 850 tells it to go counterclockwise. And the 122 says for 3 seconds. Alright, so now it's time to run the same test on the left wheel. This involves modifying the program we wrote to do pulse out to pin 13 instead of pin 12. Alright, so all we have to do is change that pulse out command to from pulse out 12 to pulse out 13 like this. And so then when we observe it, we should see that the wheel does in fact go clockwise and counterclockwise. However, what you should notice while watching this is, because it's on the other side, clockwise and counterclockwise is actually opposite directions from the right side. So the left and right sides are kind of opposite in directions. Alright, there is some information here about troubleshooting the servos. We'll just skip over that. and we'll consult that if we have troubles. Okay, activity 3. Start reset indicator circuit and program. All right, when the voltage supply drops below the level a device needs to function properly, it's called a brownout. The basic stamp protects itself from brownout by making its processor and program memory chips go dormant until the power supply voltage returns to a normal level. A drop below 5.2 volts at the VN results in a drop below 4.3 volts at the basic stamp's internal voltage regulator output. All right, the circuit called a brownout detector on the basic stamp is always on the lookout for this condition. That would be when it drops below 4.3 volts. When the brownout occurs, the brownout detector disables the basic stamp's processor and program memory. When the supply voltage comes back above 5.2 volts, the basic stamp starts running again, but not at the same place in the program. Instead, it starts from the beginning of the program. This is actually the same thing that happens when you unplug the power and plug it back in, and it also is the same thing that happens when you press and release the reset button on your board. When the Bobot's batteries are running low, brownouts can cause the program to restart when you're not expecting it to. This can lead to some really mystifying Bobot behavior. In some cases, the Bobot will be running whatever course it's programmed to navigate, and all of a sudden it might seem to get lost and go into an unexpected direction. If low batteries are the cause, it could be the fact that the Bobot's program went back to the beginning and started all over again. In other cases, the Bobot can end up doing a confused dance because every time the servos start turning, it overtaxes the already low batteries. The program attempts to make the servos turn for a split second, then restarts over and over again. These situations make a program restart or reset indicator an extremely useful diagnostic device as well as a useful robot tool. One way to indicate resets is to include an unmistakable signal at the beginning of all the Bobot's programs. The signal occurs every time the power gets plugged in, but it also occurs every time a reset due to brownout or by the button occurs. One effective signal for reset is a speaker that emits a tone each time the basic stamp program runs from beginning or resets. All right, so there's a note here about the homework board. It says, although the reset indicator will tell you when the 9-volt battery supply, the basic stamp is running low, it will not tell you when the servo supply or battery pack is running low. You can always tell when your battery pack is running low because the servos will gradually move slower and slower during normal operation. When you observe this symptom, replace the dead batteries with new ones or recharged batteries. Okay, so it's going to look different on a couple of our boards here because we have the two different boards. On the homework board, it's going to have the 9-volt battery and the 6-volt AA battery pack on the bottom. And on the new boards, the Board of Education, everything's going to come from the 6-volt. So the behavior on the Board of Education is going to be it resets as the servos are pulling the battery low. And on the homework board, since it's on a separate battery, the servos will go slower and slower, but the Bobot won't reset. So just a couple things to look out for. Right, this exercise will introduce a device called a piezoelectric speaker, or piezo speaker. Okay, you can use that to generate tones. The speaker can make different noises or tones depending on the frequency of high-low signals it receives from the basic stamp. The schematic symbol and part drawing for the piezoelectric speaker are shown in Figure 316. This speaker will be used for emitting the tones when the basic stamp is reset in this activity as well as the rest of the activities in this task. So over here on the left portion of figure 316 is the schematic symbol for the piezo speaker, and on the right here is just the diagram for it. Okay, a couple notes here on the speaker. What is frequency? It's the measure of how often something occurs in a given amount of time. Okay, so usually we think of that as in seconds, and a 1 second interval is called 1 hertz. And then you have thousands of hertz, which are kilohertz. And so those are going to be the ranges we're going to be looking at here, but it goes up to millions of hertz as megahertz, and billions, which is gigahertz as well. Okay, what is a piezoelectric element and how can it make sound? Alright, so a piezoelectric element, it's a crystal that changes shape slightly when a voltage is applied to it. Another way of saying that is it vibrates, like a quartz crystal will actually vibrate when you put voltage on it. Alright, by applying high and low voltages to piezoelectric crystal at a rapid rate, it causes the piezoelectric crystal to rapidly change shape. The result is a vibration. Vibrating objects cause the air around them to vibrate also. This is what your ear detects as sounds and tones. Every rate of vibration has a different tone. For example, if you pluck a single guitar string, it will vibrate at one frequency and you will hear a particular tone. If you pluck a different guitar string, it will vibrate at a different frequency and make a different tone. Piezoelectric elements have many uses. For example, when force is applied to a piezoelectric element, it can create voltage. Some piezoelectric elements have a frequency at which they naturally vibrate. These can be used to create voltages at frequencies that function as a clock oscillator for many computers and microcontrollers. Okay, so there is lots of neat things you can do with piezoelectric. You can actually make actuators, things that will open and close valves, like for controlling a car, for controlling fuel on a car, for example. And they actually have ability now with piezo pressure plates to actually harvest energy from people doing things like walking on a pressure plate. All right. Parts required. Okay, we're going to have our assembled and tested Bobot, and then we're going to add the piezo speaker, and I guess there's a couple of jumpers we'll use too. Right, if your piezo speaker has a label that says remove seal after washing, just peel it off and proceed. Your piezo does not need to be washed. Alright, building the start reset indicator circuit. Figure 317 shows piezo speaker alarm circuit schematics for both the Board of Education and the Basic Stamp Homework Board. Figure 318 shows a wiring diagram for both. Always disconnect the power before building modifying a circuit. Alright, so yeah, we've been saying that, but on the Board of Education that means put the 3-position switch to 0. And on the Basic Stamp Homework Board, we just disconnect the 9-volt battery by taking it out of the clip, unclipping it. Alright, so it's a pretty simple circuit we build down here. So you can see off of pin 4, we're just going to basically put a jumper out to the piezo speaker, and then the positive side's going to go to pin 4, and the negative side's going to go to ground or VSS, the negative side of the battery. Alright, the piezo speaker and servo circuit will remain connected to your board for the rest of the activities in this text. All circuit schematics from this point onward will show circuits that should be added to the existing servo and piezo speaker circuit. Right, so basically, now that we've get this basic circuit down with our servos connected and our piezo speaker, it's going to stay there basically for the rest of the semester, so you don't have to rip that up after every class. Just leave it there, and we will just add on to it for like the different sensors when we get into that later on. So again, we have our 2 different board views here, Board of Education on the left, Homework Board on the right. And basically the big difference is the servo and the servo power. So yeah, we just put a jumper wire out. They just arbitrarily chose green to the positive side of the piezo speaker, and then the negative side will be tied back up to the negative side of the battery, or VSS. So the positive side down there, negative side up here. They used a black wire. Notice that these black wires are all tying to VSS. Usually black connotates the negative side of the battery. Okay, so programming the start a reset indicator. The next example program tests the piezoelectric speaker. It used the freak out command to send precisely timed high-low signals to the speaker. Here's the freak out command syntax. You do a freak out, and then you give the pin. We're using pin 4 here, so we'll use pin 4. The duration, how long that signal is going to last, or the sound is going to last. And then you actually have a list, comma separated list of frequencies, but you can just use one frequency for what we're doing. If you use multiple frequencies, it'll actually mix those. Alright, here's an example of freak out command that's used in the next example program. So this is going to do a 3 kilohertz frequency to pin 4 for, I believe, 2 seconds. I think duration is probably in milliseconds. Let's see. The pin argument is 4, meaning that the high-low signals will be sent to the I/O pin 4. The duration argument, which is how long high-low signals will last, is 2000, which is 2000 milliseconds, or 2 seconds. The freq 1 argument is the frequency of high-low signals. In this example, the high-low signals will make a 3000 hertz or 3 kilohertz tone. Okay, so normal like voice audible range of hearing is up to around 5000 kilohertz. They can go higher, but this is going to be a good mid-high kind of tone that you're going to hear at 3 kilohertz. Okay, frequency can be measured in hertz. The hertz is a frequency measurement of how many times per second something happens. 1 hertz is simply 1 time per second, and abbreviated 1 Hz. 1 kilohertz is 1000 times per second, and is abbreviated 1 kHz. Freak out digitally synthesized tones. The freak out command applies high-low pulses, varying duration, that makes the piezo speaker's vibration more closely resemble natural vibrations of musical strings. Alright, example program, start reset indicator BS2. This example program makes a beep at the beginning of the program. When it goes on to run the program, it sends debug messages every half second. These messages will continue indefinitely because they are nested between the do and loop commands. If the power to the basic stamp is interrupted while in the middle of its do loop, the program will start at the beginning again. When it starts over, it will beep again. You can simulate a brownout condition by either pressing and releasing the reset button on your board, or disconnecting and reconnecting your board's battery supply. Alright, there's some notes in here on learning more about doing sound. I do want to say that the piezo, they work well at certain frequencies, so if you want to try and get into and do a lot of different sounds, you're going to find that it will not really make the whole range of sounds that they propose you try, essentially. So different notes just really aren't going to come out of the piezo because the material itself just wants to vibrate at a certain frequency, and when you try and vibrate it at different frequencies, either the sound will get softened or it might not even sound as you would expect it. So sometimes you might try a lower frequency and it sounds higher, or a higher frequency and it sounds lower, and that's just because it doesn't have a real good dynamic range. It's really meant to vibrate kind of at one frequency. They even call it a buzzer. It's not really a real speaker. Alright, so here is our code here. There's a debug saying CLS, I think, clears the screen, and then it's going to put out this beep, and then it's going to do the 3 kilohertz for 2 seconds as the restart indicator. And then they just are going to put in waiting for reset and pause for half a second. They're just going to do that in a do while loop over and over again. So it's going to print that out every 5 seconds forever until you actually reset it somehow by either the reset button or taking out the battery. The last activity for today will be to test the speed control by using the debug in the terminal. In this activity, you will graph servo speed versus pulse width. One thing that can make this process go much more quickly is the debug terminal's transmit window pane, which is shown in figure 319. So yeah, down here is what it looks like. It's a little bit interesting in that they actually split off the transmit and the receive. So the transmit is up here at the top, meaning when you want to enter something to the Bobot, you click in the top white box and enter it, and then what you receive kind of pops down here on the bottom. And that is very kind of unusual. Usually it's together, and you see the things that you type get echoed back to you on the same screen. And this split mode is something that you have to kind of get used to. It's unusual. All right, so yeah, the idea is we're just going to send messages to the basic stamp to tell what pulse width to deliver to the servo so that we can test the speed of various pulse widths. Okay, a pulse width is a common way to describe how long a pulse lasts. The reason it's called the width is because the amount of time the pulse lasts is related to how wide it is on a timing diagram. Pulses which last longer are wider on the timing diagrams, and pulses which last for shorter periods of time are narrow. Okay, the debug in command. By now you're probably familiar with the debug command and how it can be used to send messages to the basic stamp to the debug terminal. The place the messages are viewed is called the receive window pane because it is the place where the messages received from the basic stamp are displayed. The debug terminal also has a transmit window pane, which allows you to send information to your basic stamp while program is running. You can use the debug in command to make the basic stamp receive what you type in the transmit window pane and store it in one or more variables. Okay. The debug in command places the value you type in the transmitted window pane into a variable. In the next example program, a word variable named pulse width is used to store the values the debug in command receives. Alright, so we're going to set up a new variable here. We're going to name it pulse width. Remember, we use the keyword var to declare, and then we give it the size of the variable as a word, which is the range from 0 to 65,000. Now, the debug in command can be used to capture a decimal value that you enter into the debug terminal's transmit window pane and is stored in pulse width. Okay, so we do that by saying debug in, and DEC apparently means decimal, meaning that it's going to be a digit value from 0 to 65,000 in our case, and then we give it our variable to store it in. So yeah, again, this is saying get the value of a decimal from the terminal and store it into the pulse width variable. You can then program the basic stamp to use this value. Here it is used in the pulse out command's duration argument. So here we have a pulse out to pin 12, which was one of the servos, and we give our variable pulse width. So for example, if you said 750, If you type that into the transmit terminal window, the debug in command would store 750 in this pulse width, and then when you did a pulse out with that pulse width, it would be replaced by 750, which would be the stop signal, so your servo would not move. Okay, example program, test servo speed. This program allows you to set the pulse width, pulse out command's duration argument by entering it into the debug terminal's transmit window pane. Alright. Okay, note here, we're still going to keep the Bobot sitting on its nose so that the wheels don't touch the ground, so it doesn't wander off or go off the bench. Okay, and then it says to basically start with 650 and verify that the servo turns clockwise. Okay, and then it says next try 850 and look for it to go counterclockwise. And they say to try and measure how far it goes by placing a mark on the wheel so that you can see how far it turns. So that you'll get a revolutions per minute if you do it that way. Alright, it says we're going to use our program with all these different widths, and we're going to see how far the wheel turns for each of those. And basically we're going to give it a 6-second pulse, and in order to get a revolutions per minute, we'll multiply our value by 10, because 6 times 10 is 60 seconds or 1 minute, and then we'll figure out how many revolutions per minute by doing that. Okay, here's the example program here that we're going to use. So let's just look at the breakdown down here. There are 3 variables: declared counter, that's going to be used for the for next loop; pulse width, it's going to be used to take our values in from the terminal with the debug in command, and then put them out with the pulse out in order to make the pulse width go to the servos to control the servo. And then this pulse width comp, which stores the value that is used in the second pulse out command. Okay, I'm not sure what that is just yet. Alright, the freakout command is used to signal that the program is started. Oh yeah, that's, remember, pin 4 is where our speaker is at, and it's the 3 kilohertz signal. The remainder of the program is nested within a do loop, so it will execute over and over again. The debug terminal's operator, that's you, will enter a pulse. The debug in command stores this value in the pulse width variable. So here it's going to prompt you by putting enter pulse width out to the transmit to the receive side of the terminal, and then it's going to wait for you to do to put a number and then hit enter into the transmit window. So that debug in will get a decimal value, and then it will store it in the pulse width variable. Alright, to make the measure more accurate, 2 pulse out commands have to be sent. By making one pulse out command the same amount below 750 as the other is above 750, the sum of the 2 pulse out duration arguments is always 1500. So that would be 1.5 milliseconds, I guess. That ensures that the 2 pulse out commands combined to take the same amount of time. The result is that no matter the duration of your pulse out command, the for next loop will still take the same amount of time to execute. This will make the RPM measurements you will take in your turn more accurate. Right, so they're going to send the pulse widths for 6 seconds, but this comp is going to compensate for any changes in the pulse width relative to 1.5 milliseconds, so that the overall time doesn't get skewed when you use a smaller, narrower pulse width, or a larger pulse width for that matter, apparently. Alright, this next command takes the pulse width you entered and calculates the pulse width that will make 1500 when the two are added together. If you enter a pulse width of 650, the pulse width comp will be 850. If you enter a pulse width of 850, the pulse width comp will be 650. If you enter 700, the pulse width comp will be 800. Try a few other examples. They will all add up to 1500. Okay, so I was wrong on that being 1.5 milliseconds. It's actually 3 milliseconds. But the idea is kind of the same. A for next loop that runs for 6 seconds sends pulses to the right, the pin 12 servo. The pulse width comp value is sent to the left, pin 13 servo, making it turn in the opposite direction. Okay. Right, so the counter going from 1 to 244, that is going to make it last for 6 seconds. And apparently that's because we have a 20 millisecond pause plus 3 milliseconds, 23 milliseconds times 244 is apparently around 6 seconds. Okay. And then they have an advanced topic that we can get into if people have time, or we can just skip it. But it's basically showing here what it would look like if you graphed out your data. So they give example on the height here. They show the RPMs, and on the width axis, the x-axis here, we have the pulse widths. So the idea is the stop, or 1.5 millisecond in the middle, has a zero velocity. Zero velocity means it's not moving. It's not accelerating or decelerating. It doesn't move one way or another. It's just stopped. So the smaller the pulse widths here, the more counterclockwise it's going. So the faster counterclockwise it's going, and the larger than a 1.5 milliseconds, the faster it's going in the other direction, so clockwise apparently. But notice that they kind of taper off here at around 1350 on the low side, around 1650 on the high side. Don't worry if that didn't make sense, by the way. Okay. Alright, remember the pulse out command duration is in 2 microsecond units. Pulse out 12 of 650 sends pulses that last for 1.3 milliseconds to pin 12. Pulse out 12 of 655 is a 1.31 millisecond. And pulse out of 660 is 1.32, and so on. Okay, don't worry about that too much. Alright, so what we can do is we can send some of these pulse widths. Would have been nicer to have these in our actual duration times that we enter into the terminal, but we can fill in some of this table by running our program in class. And the idea is just to see if you can get a feeling for basically the different pulse widths. You know, if you make it larger than 1.5 milliseconds, does it, you know, if it's just a little bit larger, does it move slowly? If it's, significantly larger, like 1.6 milliseconds, does it move much faster? If it was at 1.51, was it slow? And also on the other direction, if it was at 1.49, was it real slow? If it was 1.3, was it very fast in the other direction? And so that's kind of the idea. Getting an exact RPM isn't essential at all. We just need to kind of have an idea for what's going on and understanding it. And that's basically it for this session. If we get some of that done, we'll be looking pretty good for doing some dead reckoning next week. So we'll be doing some basic maneuvers like having the robot just turn around, or going straight for a certain number of inches or feet, or making a left-hand turn. Things like that we'll be doing next week.